Now the steps for using the limit comparison test are very similar to the steps we used for the direct comparison test. For both steps, in fact, the first step is exactly the same, which is we must show that the a sub n's, which are our given addends, are positive on the interval of our summation. The second step is also the same as it is for the direct comparison test. What we need to do is use the concepts of rate of growth to find a comparable function b sub n, where the sum over the same interval of the b sub n terms is known. And by known, we mean either to be convergent or divergent, not known in its actual value. The third step is where we actually differ from what we did with the direct comparison test. Because we're performing the limit comparison test, the third step here is to compute this limit as n approaches infinity of a sub n over b sub n. We then need to follow one of the three branches from the limit comparison test stated in the previous set of videos, but in the case that we're in that first branch and we get a value for L that is strictly in between 0 and infinity, then we will be able to conclude that the two series, our given series and the series of our invention, have the same behavior. And because we're hopefully comparing to a series where we know whether or not it's convergent or divergent, this should get us some results. As an example, let's look at the series that is given here, where these terms are our a sub n terms. We wish to perform a comparison test on this series given its complexity. And given the complexity of these terms, it seems like it might be difficult to argue whether or not this is greater than or less than the thing we would like to compare it to. So it's a really ideal candidate for the limit comparison test because of the fact that it's a little more complicated. Now, taking a look at the a sub n terms that we have right here, the first thing we need to do is argue that they're positive. Well, our numerator is a cubic, and if we were to expand out this denominator, our leading term would have degree 2 plus 1 plus 2. In other words, we'd have a fifth degree polynomial or a quintic in the denominator. And both of these polynomials, the cubic and the quintic, are odd functions. Consequently, if we take the limit of each of them separately as n is approaching infinity, both of those limits will be positive infinity, and therefore eventually there's some sort of value for which this function will be positive and this function will be positive, and therefore the ratio of those two things will be positive. Now that's a very hand-wavy argument. It is true and is enough to show that you've thought about it. However, if you'd like to be more specific, we could head on over to Mathematica and we could use Mathematica's solve command, or in the case that you want numerical solutions, Mathematica's nsolve command, to ask where that numerator will be equal to 0. Mathematica then solves that and tells you that the numerator of our addends will be 0 at about -1, 0, and 1. So if you imagine a cubic making roughly this shape, passing through the x-axis at about -1, 0, and 1, after n is equal to this value, this function will always be positive. And we could do a similar thing with the denominator of the addends that we were given to find the zeros of that function, 2 of which are complex numbers, 2 of which are 0, and 1 of which is 2. Therefore, as long as n is larger than 2, our denominator will be positive. And returning to our slides, notice that we're on the interval from 3 to infinity, so this function is positive on this whole interval. The next thing we want to do is come up with our comparable function that we believe has the same rate of growth as our addends. Because this is a rational function, this is something we've practiced previously, and because we've thought about the leading degree of both numerator and denominator in part 1, our comparable function for rate of growth should be an n cubed divided by an n to the fifth, or in other words, a 1 over n squared. So in our heart of hearts, we believe that this complicated series, no matter how messy, should have exactly the same behavior as the series with addends, 1 over n squared. That series would be a convergent p-series, since our p-value would be greater than 1. So in our heart of hearts, we believe this is a convergent series. Now the way we're going to justify that is with the third step of the limit comparison test. Here, what we need to compute looks a little terrifying at first. It's the limit as n approaches infinity of the addends that were given divided by the comparable addends we previously introduced, which is 1 over n squared. If we eliminate a fraction of a fraction by multiplying by a reciprocal, this turns into the limit that we have demonstrated on the right, and you'll notice that the n squared term in the numerator should now cancel with that leading n squared term in the denominator. That gives us that this big old limit right here, which is the ratio of the terms, is equal to the limit as n approaches infinity of this much nicer looking expression. Now, we've studied these types of limits before when we studied rational functions, and the rule we had for computing these limits was to take the leading terms from both the numerator and denominator and make a ratio there, and in the limit, these two functions will have the same behavior. The limit over here is much nicer computationally. It's blatantly equal to 5. So altogether, we took the limit of the ratio of the two sequences of addends, and we got the number 5, which is strictly in between 0 and infinity. Therefore, we're in the first case of that limit comparison test, which allows us to conclude that the series we were given and the much, much nicer p-series, the sum as n goes from 3 to infinity of 1 over n squared, have the same behavior. And as we've mentioned before, this is a p-series with a p-value that's greater than 1. This series is convergent, and therefore, by the limit comparison test, the given series we had is convergent also. Now I do need to end with some very sad technicalities, but these may be things that you're wondering, and I'd like to get them off of your mind before ending the video. In the textbook that we're currently using, I've seen a weird obsession by the online homework mechanism to try to force this limit value to be equal to 1. And that's not wrong, it just differs a little bit from the way that we presented things here. So for example, I feel very confident that your online homework system would have chosen the comparable function not to be 1 over n squared, but to be 5 over n squared. And that's a reasonable comparison to make. In my case, I got a limit of 5, but if I would have compared to this particular function, I would have gotten a limit value of 1. So just be on the lookout for that as you do your homework. Another thing I'd like to point out that very frequently when you use the direct comparison test as opposed to when you use the limit comparison test is a matter of preference. Now there are examples we can cook up if we really want to of series where you can use the DCT but not the LCT and vice versa, so they truly are different tests. But practically speaking, they're very frequently interchangeable. However, this is an example of where the LCT was really and truly necessary. Again, if we step back to Mathematica, I've gone ahead and plotted both of our functions, the 1 over n squared and the function we were given. And according to the key, the function that we were given is actually larger than the 1 over n squared. So because we were trying to show convergence and the 1 over n squared is the nicer function, we would have wanted that nicer function to be above this function in order to apply the direct comparison test. Now you might be thinking, what if I change the 1 over n squared to a 5 over n squared, like the book would have wanted me to do, and it still makes absolutely no difference. All that's happened is that the functions have gotten a little bit closer together, but still our given function is above the 5 over n squared function, and so we would not have been able to apply the direct comparison test. We would have simply had the wrong picture in that circumstance. Last but not least, when we discuss p-series, we almost always start the sum of that series at 1. In this particular example that we just did, we started summing our series at 3 instead of at 1. This is truly okay because we're no longer concerned with the actual sum of the particular series. What we're concerned with is the sum finite or is the sum infinite? So in our example, 1 over n squared, we had a convergent series. It's true that when we change this series to start summing at 3 instead of summing at 1, we will get a different numerical value for what the sum of that series is. However, we will get a numerical value, and so this converges, as does the series starting at 3, so we don't really pay much attention in general to where the series starts counting any longer. Similarly, if we would have had a divergent p-series, where this was adding up to infinity, simply subtracting the first 2 terms from that isn't going to change the fact that it still adds up to infinity. And so when we take away a finite number of terms from any sum by just not starting at 1 and instead starting a little bit later on, something that converged will still converge and something that diverged will still diverge. So it seems like maybe it's a bit of an issue and it might be on your mind, but truly that's a thing that's okay for us, is to start summing at slightly different starting points.